And here's where I'm not sure how they would expect you to move on from here. If you know what the formula is, which we do because I gave it to you yesterday and it's written in the textbook, then maybe with a really, really keen insight, you could think of what to do. But I think it would be really hard. So let me think about this for a minute. Here, let me scroll down. Take a look at the formula for tan of A plus B. There it is. And it's got this 1 in it. Identities in general is all about looking for clues and looking for little things. Well, how am I going to come up with that 1? So here's the insight. If I multiply by 1 over cos A cos B over 1 over cos A cos B, when I multiply this part by that, it's going to give me a 1. Oh, that's super obvious. Everybody would have come up with that on their own, right? Like, of course. Who wouldn't see that? That's a hard thing. I mean, if you're not used to deriving formulas or doing proofs, I don't know how they would expect you to come up with that. Anyway, if we do that, everything works out really nicely and it's really easy. So let's take a look. It's a little bit, the next line's a little bit long, but then it really simplifies after that. So in other words, this is going to be like, just watch, it's going to be like this times this and times that. If I distribute, if I multiply the top, I'm going to distribute it into both. I'm not going to show that step because it would take way too long. So this is like sine A cos B over cos A cos B plus cos A sine, B over cos A cos B, all over there's my 1, cos A cos B over itself, minus sine A sine B over cos A cos B. That looks good. And if you don't see it yet, look what happens. Cos B over cos B, 1, gone. Cos A over cos A, 1, gone. What's left? What is sine A over cosine A? Tan. Nice. What is sine B over cos B? Tan B. Nice. So we can put this back into tan form, which is kind of what we want. This is 1. And what is this? Sine A over cosine of A times sine B over cosine of B. So tan of A times tan of B. And that's our formula. So it equals sine A over cos A is tan A plus sine B over cos B is tan B over 1 minus tan A times tan B. Beautiful little bit of thinking in algebra there, but really difficult to, again, magically come up with this thing that you multiply by. I don't know how. Maybe you would. Okay, so anyway, that's just where it comes from. It's kind of nice. So again, you just want to know this formula and the other formula. And again, like tan A plus B and tan A minus B have very similar structures. It's just the signs that are different. And in this case, the sign matches the sign in the numerator. So A plus B is tan A plus tan B. And tan A minus B is tan A minus tan B on top, right? The signs flip. So I think that's an easy way of thinking about it. Think about the signs. All right, so we're going to come back to that in a moment. You learned how to distribute binomials in grade 10. And you would do binomials like x plus 2, x minus 3. So why is this like that? Well, x plus 2, those are not like terms. You can't add them together. So the only way we can manipulate it is by like multiplying distributive property, binomial distribution, something like that. And this is the same because 2 plus root 3, we don't call them not like terms, but they are essentially that way. We can't add them together as exact values because one's a radical and one's not. So we can't, so it's as if they're not like terms. Okay? But we can do algebra stuff with them. So let's just see what happens here. 2 times, so I'm going to go like this, and like this, and like this, and like this. Okay? 2 times 2 is 4. 2 times negative root 3 is negative 2 root 3. Root 3 times positive 2 is plus 2 root 3. And positive root 3 times negative root 3 is going to be negative root 3 times root 3, or root 3 squared, which is what? Right? Okay, we'll get there in a second. Does this look a little bit familiar? 2 plus something, 2 minus something, same something. Some difference product. It's like the opposite of the difference of squares, right? It's a factored form of a difference of squares. You see that? X plus 3, x minus 3. X minus 9. X squared minus 9. So same idea. So these two add to 0. And I get 4 minus root 3 squared. What's root 3 squared? 3, right? Opposite operations. So this is 4 minus 3, which is 1. So we have this problem, and again, it starts in grade 10, where if we want an exact value of something, and there's a radical like square root of 2, we can't, like there's nothing we can do. We're stuck with the square root of 2. But in this case, we had radicals, and when we expanded, they're gone. And now I have an exact value of 1. So that's an important thing to be aware of. We're going to use it in a few moments. Let's just try another one. This is the same idea, but it's 2 minus root 3 times itself. So 2 times 2 is 4. Minus 2 root 3 minus 2 root 3. And negative root 3 times negative root 3 is plus 3. So I skipped a bunch of steps there, but that's the whole point. You multiply radicals like by itself, you're squaring it. The radical part's gone. In this case, square root. 4 plus 3 is 7. And negative 2 root 3 minus 2 root 3 is, this is like, those are like terms. So that's like negative 2x minus 2x. So it's negative 4x, but my x is actually root 3. In that case, I still have a radical, but that's life. Everybody okay with that? Yes? Okay, so what's the point? Okay, this is something we already know how to do. Put each of the following in proper final form. Times root 5 times root 5. Sorry, I'll let you write that down if you want. Ooh, that's got a title too. Has anybody ever heard of a conjugate? You've heard that word before. Have you ever used one? In what? Oh, really? There you go. Wow. Almost like it was the 7. So this is a radical conjugate. Not yet. C is a radical conjugate. A and B are just warm-ups. Okay, so this is one we already know how to do. This is 4 root 5 over root 5 times root 5, which is 5. So that's proper final form because the denominator is now a rational. The whole thing's not irrational because it's still have a irrational number on top, but we like the bottom to be rational. Okay, so what about if, it's a little bit different? Root 3 over root 3. That's going to give me 2 root 3 plus 3 over 3. You don't have to rewrite this, but often we write it this way just because it's sort of a standard, and we're always careful about where the square root or any root symbol ends. So if it's in the last spot, then it doesn't matter. But you don't have to rewrite it the top that way. Okay, so we kind of already know how to do that. What about this? What about when I have a sum or a difference in the bottom? How do I get rid of that radical? This is where we use our really cool conjugate. And I multiply by 3 plus root 2 over 3 plus root 2. So it's 3 minus root 2. The conjugate is 3 plus root 2. I multiply by that. And that will rationalize our denominator, because we saw in that other example that it gets rid of the radical part. Only in the denominator, though, not in the numerator. That won't happen in the numerator. We're going to be stuck with it in the numerator, and that's life. That's okay. So 2 times 3 is 6 plus 2 root 2. And if you have to do this the long way, that's fine. But once you kind of get it, this is 3 times 3, which is 9. And then it's going to be minus, because this is like a difference of squares, so it's always minus. And then root 2 times root 2, which is 2. So that's 6 plus 2 root 2 over 7. And in this case, we're done. Often we're going to find that it will actually kind of factor and reduce a little bit further. But in this case, it didn't. Any questions? Okay, so all of that was important because when we do these questions with tan, we need this skill. Okay, so is everybody okay with that? I think it's a fairly simple concept. You got to get the algebra kind of right, and you got to just remember what the conjugate is. Same terms, same numbers, opposite sign. Okay, you got this written down from yesterday, or if you don't, you can quickly sketch it. We're going to do one example, tan of pi by 12. Okay, before we get started, if you want to watch, I'm just going to go over one thing, because why not? So imagine we have 1 over 4 plus 1 over 3. I need a common denominator, so I multiply this times 3 and times 3, and I multiply this times 4 and times 4. I don't think you have to write this down, that's for sure. So this is 3 over 12 plus 4 over 12, and now when you're visualizing, which is 7 over 12, you can see how it's A plus B over A times B, right? When it's 1 over A plus 1 over B. So what if it was 1 over 3 minus 1 over 4. Same thing, multiply times 4 times 4 times 3 times 3. And I get 4 over 12 minus 3 over 12, which is 1 over 12. A minus B over A times B, but again, I said this yesterday, you got to watch out for which one's bigger, A or B. It's not quite as obvious and intuitive, but it's kind of close. So when I see 12 and I see a 1 on top, whether it's negative or positive, 4 and 3 have a common denominator of 12, and they have a difference of 1. So that's pointing me in that direction. This doesn't always work, but it's a nice little way of thinking about it. So this is tan of pi by 3 minus pi by 4. So use our formula. So that's tan of pi by 3. Order counts here, obviously, minus, whoops, what am I doing? Tan of pi by 4. Same sign on top, over 1 plus tan pi by 3 times tan pi by 4. Opposite sign on bottom. What is the tan of pi by 3? Root 3. What's the tan of pi by 4? 1. Am I going too fast? Everybody okay? Over 1 plus, what's the tan of pi by 3? Oh, it's the same thing, root 3. The tan of pi by 4, same thing, 1. So I'm going to multiply by the conjugate, 1 minus root 3 over 1 minus root 3. Which is root 3 times 1 is root 3. Root 3 times negative root 3 is negative 3. Negative 1 times 1 is negative 1. And negative 1 times negative root 3 is positive root 3. On top, we don't expect the radical to disappear. So you shouldn't have opposite signs. You'll understand what I mean in a minute if you're not following. You shouldn't have opposite signs on top. We're trying to clear the sign on the bottom. 1 times 1 is 1. And then 1 times negative root 3 and positive root 3 times 1, that's what cancels. And then root 3 times negative root 3 is minus 3. And I get negative 3 minus 1, which is negative 4, and 3 plus root 3, which is plus 2 root 3, over 1 minus 3, which is negative 2. Okay, I'm going to do this in 2 steps. You might be able to do this in one when you're doing your work, but just so that everybody can see it, I'm going to factor out the negative on top. And then those negatives are gone, right? And then this is where I divide the 4 by 2 gives me 2, and the 2 root 3 by 2 gives me 1. So this works, whoops, not minus. This should be minus, sorry. Because I factored it out. And so that's also minus. So that should be the final answer, 2 minus root 3. And again, I could go back and punch tan pi by 12 into my calculator and punch 2 minus root 3 into my calculator and see that they are the same thing. Any questions?